All right, boys and girls, today we will be looking at section 4.3, which is called partial fraction decomposition. So, kind of combines everything of your favorites. The only thing we're not going to do that I know you're going to miss out on is graphing today. All right, so it kind of brings everything together. We're going to look at some polynomial stuff, so we need to remember how to factor. We're going to look at some fractions. So, what I want to start us with is some stuff I don't know if I remember how to do or not. So in this first problem, we have, actually these first two problems, what I want to do is kind of look at this. I want to add these fractions together. All right, so the concept's not hard. It's stuff we've done before. All right, so you'd probably be saying in your head, I can't add these fractions because the denominators are not the same. Okay, so that's correct. So let's make them the same. This x and x plus 1 have nothing in common, so I need the product of the two of them. So I need to multiply this fraction by x, and I need to multiply this fraction by x plus 1. Okay, so again, something we know how to do. So this left fraction becomes 2 times x plus 1, which is 2x plus 2 over x times x plus 1 plus x over x times x plus 1. Now I have common denominators, so now I can add combine like terms. So I get 2x plus x, which is 3x. And I get my plus 2 over, if we were to distribute, we get x squared plus x. All right, so not so bad. Same idea for the second fraction. Notice that now I have 3 denominators. Each of those 3 denominators have nothing in common. So this left fraction, I have to multiply by x minus 1 and x over itself. The middle fraction, I'm going to have to multiply by, it's in the middle here, an x plus 2 and an x over an x plus 2 and an x. And my third fraction, I have to multiply by an x minus 1 and an x plus 2 over the same thing. All right, so this problem is a little bit more complex, but it's not something we can't do if you put your mind to it. All right, so now I have, on the left fraction, I have a 4 times x minus 1. I have over, by the way, a new denominator of x minus 1, x plus 2, plus a 2 times x plus 2 over x times x minus 1 times x plus 2. And I can't use black over here because I'm going to run out of room. So let's use red. So I get 3 times x minus 1, x plus 2. Ooh, bad, ugly. You get my idea, though. Over x minus 1, x plus 2. So if I had more room, this would obviously look a lot nicer. But since everything is on the same denominator here, I'm going to put it all over the same denominator. So I get, as a denominator, x times x minus 1 times x plus 2. And I'm going to have a big, ugly fraction. Now, there is a reason we're doing this, so don't worry. We're not adding today. We're not doing that. I'll tell you what we're doing in a minute. All right, so we have 4 times x minus 1. This is actually a 4x, so I can distribute and get 4x squared minus 4x. Here again, this is a 2x, so I can distribute that and I get plus 2x squared plus 4x. And then here, we had to do a little bit of foiling. If you do some scratch work here, x minus 1 and x plus 2 is x squared plus x plus, minus 2. And then I get to distribute a minus 3. So I get minus 3x squared minus 3x plus 6. Okay, technically we've done this before, so as long as you're following along, I'm all good. Okay, so we get 4x squared plus 2x squared, which is 6, minus 3 is a 3x squared. Minus 4x plus 4x, that goes away, and I get a minus 3x. And then my only constant is a plus 6 all over. Remember, this is x squared plus x minus 2, so it's multiplied by an x there. So x cubed plus x squared minus 2x. Now, why did we just do that? It's a good question, mister. All right, so what we did was we went in a single direction. So we started with two fractions. We added them together to get a single fraction. The second one, we started with three fractions. We added it together to get a single fraction. Here's what we want to do today. We want to start with what's in the box here, the answer, and go back to what was the original sum to begin with. Now, there are some applications of this, and it usually goes to graphing, and I'll kind of mention those as we go, but notice in this bottom function, this bottom equation here, x plus 2 has a vertical asymptote at negative 2. This has a vertical asymptote at positive 1, and the other one has a vertical asymptote at 0. And it kind of tells us what's going on around those asymptotes. But remember, I told you we're not graphing here today. All right. So let's see what we're going to be doing. We're going to be decomposing fractions. So we're going to take a big fraction and we're going to decompose it into the sum and difference of smaller fractions. So it's this process of starting with a simplified answer, like what we just got in the boxes, and taking it back apart, so decomposing. That's really what decomposition means. The answer to all of our questions is going to be the sum or difference of the initial rational expressions. So your first this is kind of a how-to, and it comes easier once you start doing it. First things first is you need to factor the denominator. The numerator pieces are your unknowns, so this is the things that we're looking for. You need to simplify the equation and solve for the unknowns. All right? Now, a lot of that doesn't really make any sense until you see what an example is going to look like. So there are a lot of different types of problems here. So the first one, we're going to look at distinct linear factors, something like this. So what we want to do first, as mentioned, is factor the denominator. The denominator is x times x plus 1. Then what we need to do, this is where it kind of comes into the actual decomposition piece. Our initial function here, our fraction, 3x plus 2 over x squared plus x. Once I factor it, that's my denominators of my sum. And notice I don't know a and b. Those are my unknowns. So I've split this fraction into two fractions where my factors are my denominators. All right, so notice x times x plus 1 became x as a denominator, x plus 1 as a denominator. We're going to set both of these statements equal to each other because they are equal, and we can solve for a and b. Sometimes, like I say there in the parentheses, sometimes you have more than a and b. Sometimes you have a c and maybe a d or e or f or whatever. I don't think this textbook's going to get us too challenging, though. For the most part, we'll probably have a's, b's, and c's. But I can't guarantee unless I did every single problem. Oops. So, actually, do I have this example? I don't have this example. Let's finish this example. So if I had 3x plus 2 over x squared plus x, and I split this up, I could set these two things equal to one another. So I'm going to say these two things are equal. Well, here's what's kind of weird, is I actually want to try to add these two fractions together. So I need to multiply this by x and this by x. I need to multiply this by x plus 1 and this by x plus 1. And then what I'm going to get is I'm going to get a 3x, oops. I'm going to get 3x plus 2 over x squared plus x equals a times x plus 1. So I get ax plus a over x squared plus x, which is the new denominator here, plus a bx over x squared plus x. Now, here's what's nice about these types of problems. Since I'm solving for a and b, and you notice that all of the denominators are the same, because all of the denominators are the same, I can only look at the numerator and I can solve that equation. So I can say, okay, 3x plus 2 equals ax plus, oops, not 2, ax plus a plus bx. Now, I'm going to rearrange that right side a little bit. And what I'm going to do here is I'm going to say, well, it's not really ax plus a. I want it to actually read ax plus bx plus a. I'm even going to go a little bit farther. I'm going to factor out the x. And I'm going to put the x at the end. So I get a plus b plus a. And what you'll notice here is I have a number times x plus a number equals to a number times x plus a number, which means everything that goes with the x piece has to go with the x piece over here. That means that a, oops, not that kind of a plus b has to equal 3, because those are the pieces that go with x. And then the other a has to equal 2. Oh, that means if a is 2, that means b is 1, because I can just do substitution. That means back here, this a was 2, and this b was 1. So it was actually, this equals to 2 over x plus 1 over x plus 1. Now, was that challenging? Probably, because you've never ever seen this before. But let's look at a few examples here. Let's look at more examples. There's going to be a lot of examples, I think, today. It might even end up being a long video. Who knows? So I get 5x minus 1 over x squared minus 2x minus 15. Oops. So I'm going to factor. And I know that x squared minus 2x is actually x minus, oops, not minus 3. Be helpful if I knew what I was talking about. X minus 5 and x plus 3. So since there's only two factors, I get x minus 5 as one fraction and x plus 3 as the other fraction. And since these are linear pieces, all I have is an a and a b. You'll see what it means to be quadratic in a few minutes. Okay, so now the process. I'm going to pretend to add these functions together. Or if you think about before where we multiplied by the common denominator, that works as well, but not everybody quite grasped that. So this one I need to multiply by x plus 3. This one I need to multiply by x minus 5. And I get 5x minus 1 over x squared minus 2x minus 15 equals a times x plus 3 over my denominator. Oops, let's not use d because that's silly. Over my common denominator, I don't really care what it is actually, plus b times x minus 5 over that common denominator. Again, I don't really care because it's all the same now, which means 5x minus 1 equals ax minus 3a plus bx minus 5b. Here's what you do. You put all your x's together and all your variable or all your constant terms together. So here I have an ax plus a bx, which means I have an a plus bx. And then I get a minus 3a and a minus 5b. Now, it's a process now to figure out what goes with what. I know an a plus b goes with my 5. So I have a plus b equals 5. And then I get my constant terms, my minus 3a minus 5b equals negative 1. Now, some of you might not remember how to solve these type of equations, but this is what's called a system of equations. And what I can do is I can add straight down or subtract straight down to cancel out variables. Well, in this case, nothing will cancel if I just add or subtract. So what I'm going to do is I'm going to multiply this entire equation by 3. So I'm going to say, okay, let's multiply this by 3. So I get 3a plus 3b equals 15. And if I add now, negative 3a and 3a go away, negative 5b and 3b make negative 2b, which is a 14, so therefore b is 7. Now if b was 7, up here, that means a plus b was 5, which means a had to be negative 2. So I can kind of go back to, oops, don't want to do that. So I can go back to my original equation, my original question, and I can rewrite this as a is negative 2 and b is 7. And that would be my final answer. My final answer would be this. Oops. All right, you see it's a process. It might be a long process, but anything worth doing is not going to be short. 2 plus 7 is no longer worth doing for us. Okay, it's these type of problems that make us a better math student. All right, so let's try a second one here. 5x squared minus 12x minus 12 over x cubed minus 4x. These do get challenging. I'm not saying these aren't hard, all right? So this x cubed minus 4, I can factor out an x and I get x squared minus 4, which then means I get x times x plus 2 and x minus 2. Oh, that means we get 3 fractions. So we get an x, we get an x plus 2, and we get an x minus 2. These are all linear, so we get an a, we get a b, and we get a c, which just means it's going to get harder. All right, so let's do this a little bit different. Let's do it thinking about multiplying by the common denominator of x, x plus 2, x minus 2. So this thing cancels on the left. I'm going to get, this doesn't exist. It's not part of us now. So my denominator cancels on the left. I get 5x squared minus 12x minus 12 equals a times x plus 2x minus 2 plus b. Okay, so remember the x canceled this first one. So in the next one, x plus 2 cancels. So I get a b times x minus 2. And then you notice this kind of takes up a lot of room. And then plus a c times x and x plus 2. Oh, man. Those of you that try to rush through this math you guys are gonna kind of regret that. All right, so x plus 2x minus 2 is actually x squared minus 4. So I get ax squared minus 4a plus, if you distribute here, I get bx squared minus 2bx plus cx squared plus 2cx. So then you go, okay, where are you going with this, Mr. Nelson? All right, so I'm glad you asked. Here we go. So everything that goes with my x squareds goes with my 5. So notice I have an a plus b plus c. All right, so I have an a plus b plus c. So that's all my x squared pieces, and that's going to equal 5. And then everything that goes with the linear pieces. So I have a minus 2b and a plus 2c. So minus 2b plus 2c equals negative 12. And then everything linear goes with my linear thing. So I get negative 4a, and that's actually all I have. So I have a negative 4a equals negative 12. Well, that's nice for me because that means a is positive 3. So I can get rid of one of these pieces down here and say a is positive 3. So a equals 3. Now, the only thing that really helps me with is this top equation, this a plus b plus c equals 5. So let's do that. If a is 3, I can subtract 3 from both sides, and I get b plus c equals 2. Then this next equation, I can say, well, all of these are 2's, so let's divide by 2. So I get negative b plus c equals negative 6. And you'll notice that I can add here. So the b's go away. C plus c is 2c equals negative 4. So therefore c is negative 2. And if c is negative 2, then b was 4. And lo and behold, we get everything that we needed. So b is 4 and c is negative 2. Done. All right, so you will end up noticing here, those of you that try to do your entire assignment on one side of one piece of paper will probably not be doing that for this lesson. All right, those of you that wrote everything that I just wrote probably just might have taken up a whole sheet of paper just on those 2 examples, or the 3 that we did so far. All right, you just have to get used to doing hard math. I'm trying to get you guys to understand that we are in hard math, and not everything's going to come to you right away, but it takes practice and work. All right, so there's one type. This is what we called distinct linear factors, but what we're going to look at now is repeated linear factors. This one gets a little bit complicated. Now, I'm doing every type. I can't guarantee that you're going to get an example like this in the work anywhere, but I want to make sure I cover all the bases. All right, so here is an example of a repeated linear factor. So you need to account, when you factor the denominator, you need to account for every variation of the repeated factor. So you'll notice that the denominator here actually factors 2. If we take out an x, we would get x squared minus 4x plus 4. Which is actually equal to x times x minus 2 times x minus 2. So when we decompose, we would have 3 different denominators. We would have something over x plus something over x minus 2 plus. Now we don't want to repeat the same thing because then it wouldn't work, but we would want an x minus 2 squared. And then again, we would just have A, B, and C. The solving is all the same. I'm not going to solve every single problem on here today. It's really going to be about the process with a few examples here and there. All right, so that's what that would look like in this particular form. And again, we would still just multiply by that common denominator, cancel everything, find your A, your B, and your C compared to the quadratic, the linear, and the constant term. So if I erase this, let's look at the other one here. This one's a little bit more challenging. X squared plus 1 times x, or x squared plus 1 over x times x minus 1 cubed. Here is where I would need an x. I would need a b over x minus 1. I would need a c over x minus 1 squared. And I would need a d, be helpful if I wrote a d where I needed a d. D over x minus 1 cubed. Now, Notice I said you must account for any of the variations. Now, in this case, you might not get an A, a B, a C, and a D. Maybe C is 0 in this case. Well, that just means this fraction doesn't exist in our final answer. And you could get that. You could get any of these things equal to 0. You won't get them all equal to 0 because that'd be silly. You'd be adding a whole bunch of zeros to get an answer that doesn't exist. All right. What if we had numbers or fractions where our denominator was an irreducible quadratic factor? What does that mean, Mr. Nelson? It means something like this. If you factor this denominator, you would get x minus 3 over x times x squared plus 3. Well, x squared plus 3 cannot factor any farther. Well, what this means is my numerator could have been linear in the first place. So when we write this as the decomposition process, we would say it would be a over x plus, we'd have my quadratic piece, and in the numerator would be a bx plus c. And note that this is only for this irreducible type, x squared plus 3, that's not factorable. You might have noticed back here on this page, I said this is a quadratic technically, but because they're linear factors, we just keep a constant in the numerator. Okay, and again, the process is still the same. Multiply by the common denominator, FOIL, distribute, and get all of your A's, B's, and C's as numbers at the end. Okay, so another example here would be this one. X squared plus 4x plus 1 over x cubed minus x plus minus 1. All right, some of you might remember how to factor this particular denominator if you think about it separately. They don't always work like this, so don't always think they work like this. I get x squared times x minus 1 plus 1 times x minus 1. So I would get one denominator would be an x minus 1, and that would be my linear term, so a constant numerator, plus the x squared plus 1, which is not factorable, so I'd have to have a bx plus c. Now you might need to remember how to do your possible rational roots in order to factor these denominators, especially when they get to cubics and stuff. But like I mentioned in the last sections, you need to remember that stuff from the last chapter. Now this one's a little bit more challenging because, again, I'm not going to solve this problem. I have x squared plus 1, all of that squared, which means this is a repeated factor, but it's also quadratic. So I would need an x squared plus 1, which would need an ax plus b. But because it's repeated, I need the other variation, which is the squared term, and I would need a cx plus d because it's a quadratic factor. These can start to get pretty ugly. Now this would just be the beginning of the decomposition again, right? So not the actual solving here. What should be the last type here is if your numerator is bigger than your denominator, and I mean by degree. So the degree and your degree. So if you have a cubic over a quadratic, and it's just like slant asymptotes, you would have to divide. Whenever I use PFD, that means partial fraction decomposition, by the way. Only works for proper fractions. Right? So proper fractions being something like 2 over 3. That's a proper fraction, whereas 3 over 2 is improper. All right? So we need to do long division in order to create, quote unquote, a mixed number, right? 3 over 2 is really 1 and 1/2, or 1 plus 1/2. And that's what we're going to do in this one. This one, if you did long division, you would notice you would only have an x squared come out. You would divide, get an x squared. And then you would get the proper fraction here. You'll note that this denominator You'll note that this denominator factors 2, as it just came up there on the bottom there. X squared plus 1 times x minus 2. So I would need to decompose. I don't need to deal with this. This goes in my answer. So this is kind of done until I come back to it. My process that I would be looking at is this. Equals a over x minus 2 plus, I'd have an x squared plus 1. Irreducible quadratic factor means bx plus c. So notice this is almost exactly as the same thing as the previous examples, only now the numerator was bigger, so I had to do division. Okay, so there are 15 problems. I want you to do all 15. We're going to spend, I think, at least 2 days on this in class. We might spend a third if necessary, but it's kind of one of those long sections that just you need to just sit down and do them. Okay? There are other examples out there. If you need to go to Desmos, search up partial fraction decomposition or fraction decomposition or partial fractions. One of those should come up with the correct video. I'll even try to link to the right video for Khan Academy. Don't get frustrated with these problems. They're long, they're difficult, but they're doable. All right, good luck. Thanks for watching. See you guys in the morning.